Okay, next we're going to look at the inverse Heaviside function. So for this, we're going to have to, this one's fine and ready to go. This one is fine and ready to go a little bit. This one's going to take a little work, so I thought I'd throw in a review problem. And this is where we're going to have to break this up, right? So first of all, when you look at this, the first thing you should notice is the denominator. And I already had it nice and factored for you. Typically, you're not going to have it factored. You're going to have to complete the square and see how it factors, whether it has a plus or a minus. If it had a minus, we would have difference of squares, and we'd factor that and do partial fraction decomposition and get two exponential stuff, because you'd have like s plus 2 minus something, x plus 2 plus something, right? And those would just be like what are called linear factors. They're just s minus a's in the denominator, and those would go back to exponentials. But when you have a plus, right, that gives you something that you can't get a real zero for. If you were to set this denominator equal to 0 and solve for s, you get a -4. Square root of -4 would be 2i, all right? You get a complex number. So whenever you have complex zeros for this stuff here, it's going to be the exponential times the sine and cosine. But when we do the exponential times the sine and cosine, the cosine wants an s minus a in the top, right? So let's start with that. I want an s minus a. My a is a -2. So s minus -2 is s plus 2. Hey, that matches the stuff in the bottom. But I changed what the function is, so I have to unchange it by doing -2. That seems real familiar, doesn't it? Isn't that kind of exactly the same thing I did with the Heaviside function? It is. But this one is easier because it's just 2 times stuff. So I'm able to get over there. Get over there. Take out the -2. 2 times -2 is -4, right? And then this one. All right. -4 plus 9 is 5. And so I get 2 times that. -4 plus 9 is the same as this. Let's double check. 2 times s, 2s. 2 times 2 is 4. 4 plus 5 is 9. Looks good. Okay.
So how do you know which like Laplace transform that you're going for? Like how do you know it's the
Because when you have a quadratic in the bottom that has complex zeros, that's going to be exponential times sine, exponential times cosine. It's going to be exponential times trig. All right. It's that plus sign right there. You see that plus when I do completing the square?
mm-hmm.
That plus tells me it's going to be complex zeros, right? Let me show you why. Equals 0. Equals -4. Get out of there. S plus 2 equals plus or minus 2i. Oh, there we go. You see that? So what that tells you is that you can't really factor the denominator nicely into real factors that you can use this form on, right? If you had a minus there, you could factor and break it up using partial fraction decomposition, and you get two exponential terms. You get something over s minus this and something over s minus that added together, and you'd get two exponential functions. But when you have that plus there, that says, nope, you can't break this thing up. All right, you can't use partial fraction decomposition because it doesn't have real zeros. All right, so that's the key tell right there, that +4. Is that all right? Ish.
Yeah, I just have to think about it a little bit more, but
That's fine. That's good. I'm glad you want to think about it more. All right. And then we're done with that one. So, oh wait, I didn't mean to do that. I meant to start a new. There. I didn't want to skip steps. That's like a classic experience in a math textbook. And it says, you know, after some calculations, and then like you do the calculations yourself, and it's like 5 pages of it. I was like, what the hell? Well, why didn't you just show me at least a little bit of it?
Yeah.
Yeah. So you can see where. So so first to do the cosine, because that one, it's just easier to do and know what you want to get. Because if you try to do the sine first, all right, it's you have to sort of backwards rig the cosine. The cosine is just, I don't know, it's just algebraically it should come first, because you just take care of the s and then you have leftover numbers. Then the leftover numbers you factor out. And where did I get that 2 from?
That from the 4?
Yeah, from the
Because
4. You take
it's
the square root of
the
4.
a squared.
That's right. So this is the a squared in the bottom. Where are you? What do they call it? Oh, they call it b squared over here on the table. This is the b squared in the bottom, and so you have to need a b in the top. So you just multiply and divide by whatever the square root of that is, and you factor that out in front, and you get your coefficient. Okay. All right, one more thing I'm going to do is I'm going to take this e to the 2s, and it's not a big deal. It's just visually, for me, it's a little nicer. Do that. Now, all of a sudden, right here, I have this right there. All right, can you see that? I have e to the negative cs times f of s, e to the negative cs times s of s. And that's going to allow us to do our inverse transform, which is the next step. Right? And part of what makes this tough is that you just got to get used to it. All right, you just got to get used to kind of how these problems algebraically work. Okay.
So how do you know that 1 over s plus 4? How do you know that's f of s?
Because 1 over s plus 4 is a really nice. Look, you'll get your, like in the Laplace transform space, the ones you're going to see all the time are 1 over s plus or minus something, which is an exponential transform, and then the exponential cosine ones, right? Or the sine and cosine, or sine or cosine with exponentials. You just kind of look at, like, you're looking for like a 1 over a linear factor, or 1 over a quadratic that has complex roots. Those are the 2 basic ones. There are other ones, but the ones we're going to see a ton are 1 over a linear factor, and some kind of like maybe a linear form over a quadratic with complex zeros, which will either be something like this or something like that. Okay. And I had the e to the minus 2s, so I know what that is. That is my Heaviside function transform. And so I just looked at whatever was left over. This is just a number, right? I have a linear factor in the bottom, and the one with the nice linear factor in the bottom is the exponential. And so I just look at the table and say, oh, that's going to be an exponential when I do the inverse transform on it. So how do you know what it is? By studying the table and getting really familiar with it, especially the key ones: exponential, exponential sine, exponential cosine, right? Those are the ones we see the most of. Heaviside, all right, we'll see that one, and then we'll also see delta quite a little bit too, but that's later. All right, tell me what my first function is when I do the inverse transform of this. What do I write first? Two. All right, I gave that one away. What's next? Let me scoot that out of the way so you can see it.
Because we're looking at the e to the at cosine bt.
Exactly. So what is it? You said e to the, what's a?
E to the 2t.
Close.
-2?
-2.
4.
All right. That exponential always
-2.
flips the sign of whatever's in that linear factor in the denominator. So just remember that. Okay. By the way, I make that mistake all the time. I forget to do that. I lose minus signs. It's like I had a Calc 2 class once where they asked if they caught enough times me losing minus signs, would I get them candy at the end of the course? I got them candy at the end of the course. It happened. All right. So what do we get here? Cosine what?
2t.
Yep, 2t. That's that square root of the 4. All right. What's my next one? Plus what?
5/2.
Coefficient. Good. Times. You got this. Go with it.
Cosine.
Is it sine?
Yeah, there's going to be a sign, but there's something else. What is it?
Look for a
Oh, it's an e to the
yeah, e to the
negative 2t.
negative 2t, right? Look, these have exactly the same denominator, right? This one and this one have exactly the same denominator. One of them has the s plus 2, that's the cosine marker. The other one has the square root of the 4, that's the sine marker, okay?
Why is it e to the negative 2t again?
Because it's s minus a squared, and s plus 2 is the same as s minus negative 2.
Okay.
Okay. And then we'll have a 2t. All right. What's this next one right here? 1 over s plus 4. What's that?
E to the negative.
e to the
there we go.
Yeah.
Negative 4t.
Negative 4t.
Good. All right. And now I'm going to help out a little bit. This e to the negative 8 is just an e to the negative 8. It's just a coefficient number, right? So don't try to make that part of your function. All right, what does this e to the negative 2s become? So let's look.
U, because
Yeah,
it's the
there we go.
Heaviside.
Absolutely. Cool. So let me put in my subscript notes.
U to the sub 2.
U sub 2 of t.
T.
But that's a coefficient function, right? So that's not the main one. Times, hey, this looks really familiar. It looks just like this one. Yeah. So that's like e to the
negative 4t.
Negative 4, but it's not t. What is it when it goes back to the original space? I'll help out.
T minus 4.
T minus 2.
T minus 2.
Yeah, it's like the number in the parentheses comes from the subscript of the Heaviside function.
Gotcha.
Right. So what this is doing is this is basically shifting your time 0 to a new spot, right? Which is like horizontally shifting the function. So this, instead of all our action starting at time 0 for this thing, it's starting at time 2. But but we're treating time 2 as like a new time 0 for this function. So we build in that time shift. It's kind of what happens. And we're done. Okay, again, I'm going to end the meeting and restart it right away. Okay, so we'll have a new video for inverse Heaviside transforms.